Let's take a look at this problem here. The airplane is traveling in a straight line with a speed of 300 kilometers per hour. When the engines A and B produce a thrust of 40 kilonewtons and 220 kilonewtons respectively. Determine the angular velocity of the plane in t = 5 seconds. The plane has a mass of 200 megagrams. Its center of gravity is located at G, and its radius of gyration about G is 15 meters. So let's take a look at this. Again, this problem we have, you could think again of the airplane being something like this. Again, we don't really need any exact picture because we're given the radius of gyration. In case we have a thrust here of 40,000 newtons and one here of 20,000 newtons. And according to the picture, these are 8 meters from the center of gravity. 8 meters here. 8 meters here. And let's calculate the mass moment. Again, G is something somewhere over here. So the mass moment, again, since we're given the radius of gyration, that's simply going to be m times the, how do they give it to us, a kg squared. So in this case, we're told that m is 200 megagrams. I like to put things in kilograms. So let's do that. And 8 meters squared. And if you put that in your calculator, you're going to get 45 million kilograms meters squared. And then we have most everything else we need. Again, that keep in mind what we're going to use. We're going to use this equation, I1 omega 1 plus the summation of the moments delta t is going to be I2 omega 2. And of course, this is going to be angular impulse and momentum. And so we just put our numbers in. Now, there's originally no angular velocity. And then so next we'll put our moment in. And so we're going to have for our moment, let's say if we count counterclockwise to be positive, that'll be 40,000 newtons, 8 meters from the center. That's going to be our moment for that one. And then we have this 20,000. So if we count counterclockwise positive, the 20,000 will end up being negative. And again, that'll be the moment for the other one. And we want to know what's going to happen after 5 seconds. And so that's going to be our delta t. And that's all equal to I. And now I's are 45 times 10 to the 6. And then our omega 2. So there's our equation. And when you put this on your calculator, you get omega 2 to be 0.0177 repeating radians per second. Now we'll take a look at this problem. The disc has a weight of 10 pounds and is pinned at its center. If the vertical force of 2 pounds is applied to the cord wrapped around the outer rim, determine the angular velocity of the disc in 4 seconds starting from rest. Neglect the mass of the cord. So let's take a look at this problem. And so this time, again, we have this, keep in mind, we're going to use this equation, angular impulse and momentum. And so let's think about a moment we're going to have here. So again, we're going to have an angular velocity like this. So think of what moment would be created. Once again, this is a constant force and the moment's going to be constant. So that's going to be, looks like 2 pounds times 0.5 and so the moment looks like it's going to be 1 foot-pound or pound-foot like this. And we want to know what's going to happen after 4 seconds. And let's see, what else are we going to need? We're going to need the mass moment of the disc. Again, it's about its center. Now it's rotating about its center, so we're not going to have to use the parallel axis theorem this time. And so it's going to be 1/2 m r squared. So it's going to be 1/2. And the disc is 10 pounds. By 32.2. And then the outer rim is 0.5 squared. And put that in my calculator. And I got 0.03882. And now we have everything we need to put this into our equation. I just want to repeat the equation down here. And again, you're starting out at rest, so this is going to be 0. Now the moment will be this moment here. I don't know. It doesn't matter if you call this positive or negative, because all it wants to know is the actual angular velocity. Just long. So I'll call clockwise positive this time. If you wanted to be consistent, and call the other way. In fact, maybe I'll do that. Let me call counterclockwise positive, because that's usually the way we do it. And so therefore, this is being pulled in the clockwise direction. So let me just put all the details. So again, since the moment's constant, this is going to be m delta t is I omega 2. And so this is going to be 1 pound-foot. And I want to know what's going to happen after 4 seconds. And let's put this in. And when you put all that in your calculator, you get omega 2 is 103.04 radians per second. For these next couple of problems, we're going to use conservation of angular momentum, because the next couple of problems, there's going to be no moment and therefore no impulse. So we're going to have just conservation of angular momentum, which means I1 omega 1 is equal to I2 omega 2. So take a look at this problem. The turntable T of a record player has a mass of 0.75 kilograms and radius of gyration of 125 millimeters. It's turning freely at 2 radians per second when a 50-kilogram record falls on it. Excuse me, 50-gram record falls on it. And determine the final angular velocity of the turntable just after the record stops slipping on the turntable. So let's take a look at this. So again, so we're going to have at the start and call it the end or the second state. Now, what's interesting this time is that we have a change in mass moment at the start and the finish. So at the beginning, the only mass was the 0.75 kilogram turntable. And we're given the radius of gyration of that turntable, so we can use just MKZ 0.75 with 125 meters. And of course, these are squared here. And when you calculate this, this is 0.125 squared times 0.75. You get 0.01172 kilogram meters squared. Actually, I should mark this. So at the beginning, again, this is the turntable. Then at the end, we're going to have the turntable as well as the record. And so turntable, from here we got 0.01172 kilogram meter squared. And then we're going to need the I of the record. Now we're assuming the record is just a disk. And so for that, because we're not given a radius of gyration, so we're going to have to use our normal 1/2 mr squared. And that's going to be equal to 1/2. And the record was 0.05 kilograms. And its radius, according to the picture there, is 150 millimeters. So it's 0.15 meters. And again, that's squared. And this is going to be 0.50, excuse me, 0.0005625 kilogram meters squared. So then let's go ahead and calculate this. Again, we're going to use conservation of angular momentum. And we have I1 omega 1 equals I2 omega 2. And our starting I was 0.1172. And our omega 1, we were told there's 2 radians per second. And our ending I is going to be the sum of these two. Times omega 2. And when you put that all in your calculator, you're going to get omega 2 to be 1.908 radians per second. Take a look at this problem. A 2-kilogram rod with 2 4-kilogram discs at its ends. If both discs are given a clockwise angular velocity of 5 radians per second, while the rod is held stationary, then released, determine the angular velocity of the rod after both discs have stopped spinning relative to the rod due to frictional resistance at pins A and B. Motion is in the horizontal plane. Neglect friction at pin C. So let's take a look at this. So kind of understand the concept of this problem, because you're going to be doing ones very, very similar. And so the basic idea is that at the beginning, just these discs are spinning, but the rod's held constant. So at the beginning, so let's say at the start, all we're really going to be dealing with are going to be the 2 discs. And because they're spinning about their center of gravity. So, and let's go ahead and find that center of gravity. And, well, excuse me, the mass moment. So it's going to be, now we have two disks. And so it's going to be 1/2 mr squared, which is going to be, the twos will actually cancel. So we'll end up having 4 kilograms times 0.15 meters squared. And when you put that in your calculator, get 0.09 kilogram meters squared. And again, at the beginning, they're turning at 5 radians per second. Now at the end, so at the end, it's going to be spinning this whole assembly is going to be spinning. And so we'll have like a center here at C. And now we're going to then like treat this. So again, this is now going to be spinning like, say, about this center. And these are not going to spin with respect to the rod. They're going to be going along with the rod, but they're not going to be spinning. So now we have to find the mass moment of this assembly. And so the rod is going to be, and that it's going to be a slender rod, 1/12 ml squared, which is going to be 1/12 2 kilograms. And that rod length was 0.75. And if you put all that in your calculator, you'll get this to be 0.09375 kilogram meters squared. Now then we're also gonna, so that's gonna be the rod. Now for the discs, the mass moment of the disc about their center is gonna be the same as before. The only thing now, we're spinning around this center, which is 0.75 meters from the center of the discs. And so we're going to have to use, again, for the discs, we're going to have to use a parallel axis theorem. Like I said, we've already calculated this over here. Again, we have, well, actually, this was for 2 of them already, huh? So actually, we're going to have to, we should go through this carefully. So again, for the mass moment of the disk, it's going to be 1/2 m4 kilograms r squared, which is 0.15 squared. Then using the parallel axis theorem, it's going to be the mass, which was 4 kilograms, times the distance of that mass from the center, which is 0.75 squared, like this. So that's going to be 2, and this comes out to, I got 2.295. So 2 times 2.295, that's a 4. 0.95 kilogram meter squared. So now it looks like we're ready to apply conservation momentum. And so we're going to have like I1, omega 1, I2, omega 2. So again, at the start, our I was 0.09 kilogram meter squared. Again, that was for both disks. Notice we included both disks. And the original angular velocity was 5 radians per second. And now at the end, we have these over here. And I think I forgot to multiply. Oh, that's right. That's only one. So it's going to be 0.9375 plus 4.59. And to make it 2. And let's calculate this. I'm getting what looks like 0.0961 radians per second.